Okay. Hello, and welcome to my talk on benchmarking S3 with Cosbench. First talk of the SDS dev room, so I'm going to try and, even though it's a talk about benchmarking, I'm going to try not to make it stale and kind of benchmarking can be a very repetitive process, so try and keep it interesting. And basically what I'm going to talk to you about today is this open source project called Cosbench, which is a benchmarking tool for object storage. I'm going to try and focus less on specific performance or results and kind of getting down into the weeds, but rather more about the open source project itself, what makes it good, what makes it bad, what makes it ugly, why we've been using it. So hope that'll be useful. So I'm sure everyone that's attending this dev room knows what S3 is. It's an object storage API introduced by Amazon in 2006, and since then has become a very popular way to put storage in and out of the cloud. And object storage vendors have been using S3 pretty extensively since then, and Ceph is no different. Ceph gives you the ability to use the Rados Gateway project to build arguably one of the best S3 offerings there is on hardware. So it's a really good project, and I work for a company called Softyme. We're building appliances around Ceph, and one of the things we're doing is focusing on S3 and figuring out what the best way to provide S3 to different environments and workloads for our various customers. As part of that is figuring out how to benchmark S3 in a number of different scenarios. So this is where Cosbench comes in. I've been doing quite a bit of work with putting together, assembling various different set configurations, and then figuring out how that impacts performance of S3 on different customer workloads. So this is kind of the background for this talk. See if I can get this slide. Yeah, there we go. So why Cosbench? There's lots of benchmarking tools out there. Not as many as you'd expect for S3, but there's quite a few. And why have we chosen Cosbench over some of the other stuff? So what else is there? We've got FIO. FIO is great all round. I'm sure most people in this room are familiar with it. It's very powerful. I've used it a lot for testing block devices and general hard drive testing, and for testing Ceph's RBD as well. It's really mature. It's really well documented. It's been around for decades. Great. Yeah, I'm a fan of FIO. I'm not gonna lie, and it has lots and lots of knobs. It can feel like a bit like being the pilot of an A380 really sometimes with FIO, and one of these knobs is the ability to use HTTP as one of the I/O engines there with libcurl, and that's really good. There's also this tool called HSBench, which came out of the Ceph community. I believe it's a fork of another tool like a Wasabi S3 benchmarking tool, but it was like rewritten, refactored to really focus on benchmarking Ceph specifically. So that's another option. There's also lots of scripts and small projects that you can find online that aren't really very mature, but just kind of some guy wrote over a weekend kind of thing that let you benchmark S3. There's also like copy tools as well that have some benchmarking features in them. But the thing about Cosbench is not only is it specifically focused on actually benchmarking S3, but the first and foremost, the most important thing to me is that it's used really, really heavily. And so every time I'm talking to a new prospective Ceph user, quite often they've been using Cosbench as well to test their own Ceph and other object storage as well. And so that means that the great thing about using Cosbench is it means that when we're comparing our work and our notes and our results, we kind of have the same things to compare. So we have the same results, we have the same workload files. We can literally just share workload files and run the same workloads, and we kind of get that like a not almost apples for apples comparison. So that's really good. The other really good thing is that Cosbench has lots of built-in support for various other object storage technologies. So it has this extensible adaptive framework, and lots of other object storage vendors have written drivers to integrate with Cosbench. So you have drivers not just for Google Cloud, but also for Scality Ring and ActiveScale and a whole bunch of others. There's about a dozen of them. And so that means not only are we benchmarking S3, but we can also compare Ceph Router's gateway and a specific configuration to other object storage technologies as well. And it will still be almost apple for apple because we're using the same tool. So those two things mean that Cosbench is more than just something that's going to give you performance results, but it's also going to be a benchmark in the true definition of a benchmark, in the sense that it's a standard that is well understood. So that's really valuable. So that's one or two things that it really has an advantage over. Thirdly, it has this controller driver architecture that scales really well. So great thing about Cosbench is that you can spin it up with lots of different nodes. I mean, I'll go into the architecture in a bit, but it scales really, really well. And it has the ability to benchmark not just S3, but also LibRados as well. So it's another good point about it. So background, it was developed by a couple of researchers out of Intel, Shanghai R&D between 2013 and 2015. It was released as open source, and some of the original design goals were extensibility and scalability. And the extensibility piece, as far as I can tell, this is the reason why it was built with OSGI and the OSGI framework, is instead of being built as one big monolithic project, what they decided to do was build it into all these different OSGI bundles that kind of spin up independently of one another and talk to each other. And so that means that new object storage vendors can write their own adapters and extend the core of Cosbench with whatever shim they need to get it to work with their object storage without really having to understand the rest of the code base. So that was kind of the idea behind the extensibility piece. And lots of people have done that, so that kind of worked out quite nicely. How is it architected? So basically, we have this controller node, and we have a set of driver nodes. Now this can be the same node. You could just get one really beefy node and run the controller and driver daemons on that same node, and then it will just be your benchmarking node. But the thing is, at some point you're going to be limited by using a single node, either on the network or CPU or memory or some way. And so even if you get the biggest, baddest node, it just today, as we know, scaling up versus scaling out makes a lot more sense to just to build your architecture in a kind of in a horizontal fashion, and then you can add additional driver nodes as you need to as your object storage gets bigger, and you always ensure that your benchmarking system isn't going to be the bottleneck when we're doing this type of work. So what do? We take a bunch of XML. It's all XML, pretty typical for a Java ecosystem kind of project. But what we do is we take some workloads, we put them into the controller pipe. There's a work queue. It takes a set of jobs, and then it runs through those jobs sequentially. So it does one job at a time. And then if we want to do parallel work within each one of these workloads, we define kind of a number of different stages. So what does that look like? I'll talk about that in a second. One thing I want to mention is kind of what our network typically looks like for a Ceph cluster. And so here's kind of a small view of what a typical kind of Ceph benchmarking workflow kind of architecture looks like. We have a bunch of Cosbench drivers you can see on the right, and they're connected to two logical networks, but it's all hooked up to the same SFP switch. In this case, it's SFP28, could be whatever you want. But yeah, we're connected to, and I've actually got iSCSI network here. Should be the S3 network, but it's same thing in principle. Is for Rados gateway, the Cosbench drivers are going to talk over in this diagram iSCSI network, but assume it's the S3 network, to the storage routers, and that's the data path basically. And then it's going to come out of the storage routers on NIC1 and go to the public network. And so from the public network, you're talking to the OSDs, and you're getting heartbeat from monitors. I mean, the gateways are talking to the monitors, but really we're talking to the OSDs directly. So why do we have another green line going to the public network from the Cosbench drivers? Because if we set up workload files that are using Rados as opposed to S3, then the storage routers aren't in the way at all. So we can basically do two different types of benchmarking. We can do benchmarking for S3 itself, and we can figure out how to architect our Rados gateways, how many we need, are we improving performance, are we reducing performance by the number of gateways we have and how we're configuring them, or and we can compare that against doing direct benchmarking against the OSDs, which in which case the Cosbench drivers themselves would be cluster aware because they have the Ceph client running on them. So that means they talk directly to OSDs. There's no Rados gateway in the way, and it's just a really good way to kind of compare and contrast S3 and see just get more data about the workflow. So what does a workload file look like? Let's see. Basically, this is how a Cosbench workload file starts. You've got this XML declaration at the top, and we have the name of the workload. We have the type of storage it is, kind of like a endpoint declaration. Basically, this is where we put our endpoint, and it's worth pointing out here as well. Another good thing about this architecture is that Cosbench has the ability to address many endpoints, and that means that different to other benchmarking systems where you usually have to give it one endpoint, and that might be behind a load balancer, or you just have to figure out a way to take a whole bunch of Rados gateways and turn them into one single addressable unit for your benchmarking tool. With Cosbench, you don't have to do that. So you could do it with load balancing, you could do it with round robin DNS, but we don't have to worry about any of that because in Cosbench we have the ability to address each endpoint. We can specify lots of different endpoints in our workload file, and it will address them. In this workload file, for what I'm doing here, I've actually just put Cosbench and Ceph and the gateways all on like the same two boxes, just to kind of give you an idea as to how it works. So really, there's just a single endpoint, which is my Rados gateway. And you can see here I've put the access key there and the secret key there, so it uses those two things to assemble the headers before it sends off the workload. And so that's kind of the start, and then we have a set of work stages, and each one of these work stages happens sequentially, so one at a time. And typically we'll have a set of work stages before we run our main workloads, and we'll have a set of work stages after. They're like pre and post kind of prep and cleanup, if you like. And so for S3, typically what we want to do is create a bucket or a set of buckets, and we want to put some objects in those buckets so that we can read and write them. Now in this case, I haven't actually even got a prepare stage, which is very typical in Cosbench to create those objects. The reason I haven't got that is because I have a write work stage first. So if this was a read-only workload, I would need a work stage because I need some stuff to write. But in this case, I'm writing first, and I'm writing a fixed set of objects. You can see total ops 100 there. So as long as I only read a total ops of 100, then I'm good. If I try and do 150 total ops read here, we're gonna experience some pain because it's going to overflow. We don't have any objects to read, so that's not going to work. It also can be, if you want to do time-based workloads, it's very important to have a prepare work stage because if you almost always read quicker than you write. So if you do any time-based workload where the reads and writes at the same time, you're going to have some sort of overflow. So you want to have a prepare work stage, but for the sake of fitting an XML file on one slide, I've skipped the prepare stage here, and you can just see that I have a bucket create, a write workload, a read, I should say work stage, write work stage, read work stage, and I have a combined read write work stage, and then I have two work stages where I'm cleaning up the objects and then I'm disposing of them. So you can see here I only actually have one work stage here where in fact actually all of the work stages here are running a single work. That's quite atypical. What you would typically do is set up lots of different work. So if you look at this 70-30 read write work stage, I'm actually running two operations in parallel, and the ratio within that specific work is 70-30 reads to writes. But it's quite typical to have lots of different works that run in parallel within a single work stage. So that's kind of why you have this work operation design. I could run many bucket creates at the same time, and then I'd have multiple works in the same line, or I could run specific write-read operations and run those as either inside a single work or as a set of works within a work stage, and they'll all run in parallel. So it's a really, really flexible way of writing workloads. And this can be very time consuming, putting these XML files together. So be wary of that. So I'm just going to go in and run a quick workload and just show you what this looks like. Let's see, how do I move over to these slides? So first thing I want to show you is I want to do a bucket list. So you can see I have set of buckets here, and yeah, just some buckets left over from before when I was doing some testing. And the second thing I want to show you is this XML file, which is the one we've just seen. Same exact thing that you've seen on the slide: bucket create, write, read, write, clean up, and dispose. So we're good with that. We've got the endpoint there, we've got the access key and secret key, so everything should be good. The next thing I want to show you is two things. First thing I want to show you is a couple of cool things. The first thing, which is we've been using Cosbench for quite a while, and lots of people within, a lot of my colleagues and some of the people I work with on these projects, it gets very tiring. Assembling XML workloads, because that, after you've done 3, you just want to automate it. It's just so slow and time consuming, and there's so many different little things to worry about. And XML sucks. Let's be honest. So we've got some Python scripts that we've put together to kind of automate the creation of these XML. That they get the job done, and then we've also put together a systemd service. So if I do system ctl status Cosbench, you can see that I have a Cosbench driver running and I have a Cosbench controller running, both on this node. So that's really cool. It's another cool thing we've done to make our lives easier. Another cool thing we've done to make our lives easier is we have this Debian package, so that my colleague Milan has created, and you can see he's got all the dependencies in here. It's really tidy, and a bit of description and kind of what it does. But this means that we can basically apt install Cosbench on our fork of Debian, and it will just work. So that's very, very useful as well, because getting Cosbench up and running can be quite painful. I'll talk about that in a bit. So let's submit a workload. I want to show you what this looks like. And what I'd like to do is actually I want to pull up the see, they're all tidily in var log Cosbench. As you can see, in here we have system logs, libs, and specific mission logs. So within the mission directory, we can see all the different logs from different workloads that have been run historically. But the one we care about right now is system. The libs is just kind of when you run, like a runtime kind of loading of all the different OSGI bundles and seeing how they interact. So if there's issues there, they'll go into libs. So that's kind of important. But system is what we want. And if I come in and so there's this command line tool and there's a web interface. The web interface, there's not really much difference because really all that both of them allow you to do is A, submit workloads, and B, either cancel an ongoing workload or kind of view your pipeline of queued workloads. So there's not much difference really between them. If I show you, I've got this CLI tool, submit, cancel, and info. So if I run info, you can see that I have 3 drivers and 0 active workloads. I'm going to submit a bunch of workloads now. I'm going to submit that like 5 times. Just keep submitting it. So now you can see, go up to the info, got a bunch of queued workloads, and that's going to start running and writing. So let me show you what the web interface looks like, just so you get an idea. go back to OBS, figure out how to switch back. That's what I want. I have to refresh this page. There we go, boom. So you can see all these tests. So one good thing is alive, not alive. I mean, yeah. Don't read too much into this actual. I mean, this is just a test cluster that I'm just running Cosbench on, just to give you an idea of what it looks like. But yeah. So I'm not sure if these drivers are alive or not. Sometimes they just report as not alive, but it doesn't really matter either way. I can go into each one of these workloads and I can kind of see what's going on. I can see the write stage, the read stage, I can see latency, bandwidth figures. I can kind of go into each one of these specific work stages and kind of view more information about it. These will link to drivers though. Will they? No, they won't. These will link to drivers and specific missions. And so you'll have to have all the right stage forwarding if your cluster's behind some sort of DMZ or NAT for each one of these drivers, which is a bit of a pain. But other than that, that's basically what this web interface gives you. So I don't use it very often. What we've done instead is we've written some parsers that go in and look at all the Cosbench logs and pull out all the information that we need, so latency and bandwidth, all the various latency results, and then we have some other way of parsing those, and so that's another really useful tool, and it means we don't really have to worry about this web interface at all. This web interface really doesn't give you very much. You can submit a workload, and then you can also, if you're a beginner and you don't really know how the workloads work, you can come in and like click a bunch of clicky buttons and drop downs, and it'll give you an XML, and it'll give you a really bad XML. Not really the way to do it. I'd highly recommend if you want to do this, go and read the docs, figure out exactly how the syntax works, and kind of and do it that way. Don't use this is just painful. So that's kind of Cosbench in a nutshell. We can see it running. You'll see also if I run that. If I run that bucket list again, you'll see that it's created this benchmark bucket for me. It does that really quickly, and then at the end you'll also see that maybe I can catch it as it finishes one benchmark, it goes to the next and deletes that, but maybe not. Where are we? We're on a read. We're just coming to the end of a read, right? Dispose. So yeah, there you go. Benchmark has been nuked. We can see we've come to the end of this like stage 6, and we're about to start another one, so the bucket should be there again. Boom. So, I actually caught it. So that's basically a Cosbench workload in a nutshell. So if I go back to my slides, what did I want to talk about? Yeah, so web interface, we've done that. Problems. So we've done the good, we've explained why we use it, explained why we care about it. I want to talk a bit about some of the problems that we have with Cosbench. So yeah, we've talked a bit about. I'll start at the bottom, right? Writing XML, painful. No one wants to do it. So we've written some tooling there to parse results and also help us generate these XML files. But there's some other problems with Cosbench. The first thing is, and foremost thing is, it hasn't seen development in like real development in 6 years. There's been some side projects and things, adding Prometheus here and doing the actual core of Cosbench hasn't really been touched in a long time, and so that's a negative. Obviously, it doesn't have a build system. So if you want to build Cosbench from source, you have to download Eclipse, figure out all the voodoo it takes to load all the different bundles and Java libraries into Eclipse, build it, not only that, the latest release doesn't build and it doesn't run. There's weirdness there. You want to go one release back. It's not in a great shape. The current upstream, it's not packaged, so there's no real way to install it easily. In fact, all of the binaries are distributed as part of the source, which is terrible. Has a bunch of these weird bash scripts to get it working, and some of them you need to put the fiddle with. I had to change a bunch of stuff in there to actually get them running in some cases. A lot of the vendor adapters that they haven't been kind of maintained very well, and so some of them are broken or don't work. And also because it hasn't been seen development in quite a while, the Java is actually that Java depends on, and quite a lot of the libraries and dependencies there are really old. And so the fact that it's not packaged really for any distro, and the fact that it's got all these its ancient dependencies, means that if you want to run it on a modern distro, you might have some issues. You might run into dependency hell. You might have to bring in like really old sources, and it's just not fun. So there are quite a lot of problems with Cosbench, but actually, like, not the end of the world, because we've kind of, some of these we've already kind of jumped the hurdle on them. We've written the tooling required to parse results and write XML. We've kind of got our own packages and systemd services, and so the main thing I think that needs repairing is the build system. So if we can figure out how to get the build system to work, I think a lot of these things could come together into a really nice patch to Cosbench, and kind of improve the state of Cosbench and make it very, very usable today. So what we've been looking at, this is kind of like a small project that we're working on, is how realistic it might be to get Cosbench to actually build from the command line with Maven. Have a bunch of like POM files, bring in all the sources and build all these OSGI bundles in a sensible way, as opposed to like depending on Eclipse or something. If we can do that, that would be really cool. And then off the back of that, we can figure out the packaging. We can figure out how to actually take some of the tooling that we've written and make it usable by other people. Maybe look at some of the adapters. Make sure that like the Bash runtime bootstrap stuff is working. So basically, I guess what I'm saying is that if we can crack this build system issue, maybe we can make a lot of these problems go away and make Cosbench kind of a much more user-friendly tool to use. I know lots of people are using it despite all these issues, which amazes me. I really, it took me quite a while to figure out how to get past all these issues. But then every time I talk to somebody, they're like, "Oh yeah, we're using Cosbench." Like, how? How are you using Cosbench? So yeah, I'm really keen to see the build system fix, if we can fix it. And if we do, we'll definitely be making that kind of publicly available and to the community, so that other people can benefit as well. So that's really the state of Cosbench today, and that's what I want to talk about. If you have any questions, please ask them in the chat. Thank you very much.